Hello everyone, this is Richard Eaton, your CTEC 134 instructor. This video is primarily to deal with normalization concepts, and it's a multi-part video that's going to start with the discussion of functional dependency. The textbook, Database Administration Fundamentals, introduced normalization concepts to you in week 1, and to tell you the truth, that's pretty premature, I think, because these concepts really require that you have some fundamental understanding of how relational databases work. The Guide to SQL textbook introduced the subject to you in chapter 2, which I think is probably also a little bit premature. But here we are now in week 4, and I'm going to expound on the subject of normalization and functional dependence. I can tell you one thing for sure. If you're going to be a database designer and going to design any database that has any reasonable complexity to it, you will not succeed if you do not understand the concept of functional dependence in the first 3 normal forms. And I'm not using hyperbole here. I truly believe that. I've seen so many students just jump into database design and create tables and put data in their tables and then find out later that the whole design structure isn't going to work at all. So this subject is really quite important. I have created a PowerPoint presentation to go along with this discussion. And the PowerPoint presentation is in Canvas. Let's see, I don't think I have Canvas running. I don't have Canvas running right now, but I do have the PowerPoint presentation running, and you'll find it in Canvas course documents. And also, there's a document that in Canvas course documents that I'm going to refer to called Important Relational Database Definitions, and we've looked at that several times. I've modified that particular document in the last few days just to make it a little bit clearer and in a bit more logical order. But let's start with the actual PowerPoint presentation that talks about functional dependence. And as I said, you can maybe download and print or study this particular PowerPoint at your leisure, or go back and reread the textbook if you don't fully understand it. Okay, functional dependence. Here's an example. Cookies. Suppose you're buying cookies and someone tells you that each box costs $5. The cost of several boxes can be computed with the formula that cookie cost equals number of boxes times 5. That's pretty logical. We can say that the cookie cost depends on the number of boxes. And the word depends is actually rather important here, because when we look at the definitions of normalization and functional dependence, you will see that they often refer to the word depends or determinant. And so the cookie cost here depends on the number of boxes, the number of boxes actually being the determinant. Here's another way of saying it. Cookie cost is functionally dependent on the number of boxes. Another way of expressing that that you often see in database terminology is that the number of boxes in this right arrow means determines cookie cost. So the number of boxes determines cookie cost. The number of boxes is called the determinant. And that's pretty straightforward. Let's look at another example. If we had a case of parts, we say we have extended price for parts depend on the quantity and unit price. So the extended price equals the quantity times the unit price. That's pretty easy to understand, I think. The extended price is functionally dependent on two things, the quantity and the unit price. Okay, so down here we could say that the quantity and the unit price, those two things together determine the extended price. The composite quantity comma unit price, those two things together, is the determinant of extended price. Okay, so let's move on. Here is a more formal definition of functional dependence. Column B is functionally dependent on column A if A's value determines a single value for B at a given time. If you read that, that doesn't really make a whole lot of sense. It's not all that clear. So we need to see some examples, which we will here in a second. Another way of saying that is, given a value of A, a single value for B can be determined. Okay, let's look at an example here. In this particular example, I'm using a test database from a prior edition of our Guide to SQL textbook. We're in 9th edition, and I believe this particular example comes from the 8th edition, and it uses a database called Premier Products, which is essentially exactly the same as the tile distributors, but the author, for some reason, decided to change the name and some of the values, but basically this particular database is identical to the one that we're working with tile database. In this case, if let's say this is the only thing we have to look at, we have this table and we don't have anything else to refer to other than this table. And we examine the first column and say that we have a Kaiser, Holland, Perez, and those are all unique. They're all different. And so given that, if I told you the name was Hall, could you tell me the commission? And you could. I mean, there's no discrepancy here. The commission for Hall is $39,216. If I told you the name was Kaiser, could you tell me Kaiser's address? And you could, in every case, without question. So you could say then that the last name functionally determines these these 7 other attributes. Last name functionally determines them. You could say that if I made the last name a primary key, and primary key values have to be unique, which they are. If I made that a primary key, I could say that the first name, street, city, state, zip, commission, and rate are non-key values. And I could say that all of these non-key values are functionally dependent on the primary key here, last name. But what if I added another row to this particular table? I added a Kaiser will. And then I said, the last name is Kaiser. Could you tell me what the city is for Kaiser? Well, you really can't in this case because there are 2 Kaisers, a Valerie and a Will. One of them is in Grove and one of them is in Norton. So in this case, the last name could not be used as a primary key, and the last name does not determine all of these other non-key values. So you could say that none of these non-key values right here are determined by the last name. What if I added an additional column to this table? I added a rep num column. And if you examine this rep num column, you can see that I haven't used any duplicate values here. So you could say, well, maybe this is the primary key. In reality, you can't always know the nature of your data just by looking at the data. You can get a pretty good idea of what the nature of the data is, but in some cases you actually have to ask your client, the person who you're working, who you're developing the database for, how rep num is used. You would have to ask them, is that a unique value? And if the client says, yep, that's it, that's how we identify individual reps, we never duplicate that value. So you could then say, well, in this case, the rep num is a primary key, and that rep num determines each and every one of these other non-key values. So last name, first name, street, city, state, zip, commission, and rate are considered non-key values, all functionally dependent on the primary key. The definition of a primary key, and we've seen that before, is that columns on which all other columns in a table are functionally dependent. So in this case, we could say that all of these keys, all of these columns from last name through rate are functionally dependent on this column. So this column can be a primary key. Candidate keys. There are times when you have two columns that have essentially the same attributes. The definition of a candidate key here is columns on which all other columns in a table are functionally dependent. It's the same as a primary key. An example of that might be, in this case, I might have a rep num value, and then I might have a social security number, and I might have also, say, an email address. And in each of those cases, they could all be considered primary keys, since social security numbers aren't duplicated and email addresses aren't duplicated. Those three columns could be in this particular table, and three of them would satisfy the conditions of a primary key. But what we do in reality is we pick one to be a primary key, because in relational databases, you can only define one primary key per table. So we pick the one we want to be the primary key, and we consider the other ones candidate keys. They have the same properties of a primary key, but we're not using it as a primary key. Alternate keys is just another name for a candidate key. Sometimes you see in definitions of keys, sometimes you see the word alternate. So oftentimes you see the word candidate. Surrogate keys are keys that are actually generated by the relational database management system. Surrogate keys will automatically generate unique values for you, and they're immensely useful in creating primary keys. We'll talk about more in the next few weeks about surrogate keys. But if it's not a primary key or a candidate key, alternate key or a surrogate key, then it's considered a non-key value. In this case here, we have a customer number that I've identified as C, and then we have customer name, city, and rep num. And we can consider the C here as being a primary key, and all of these other ones, the T values, as non-key values. And this is a fine example of a table that is constructed properly. Look at this scenario here, though. This is the same table as the prior one, but what I've done is I have added the rep's last name here. So now we have an issue. We have an issue in that this primary key does not functionally determine all 4 of these non-key values. The reason is that this non-key column here, rep num, determines the rep's last name. So the rep's last name is dependent on the rep num. It's not dependent on the customer num. So in this case, we have an issue in our design. And the solution basically is to, let's go back. The solution is to actually create a new table with a rep num and a last name and a first name and address and all that other stuff, and put it in a separate table. And in this particular customer table, we would leave the last name column out, but we would take it out, take the last name column out. We would leave the rep num column so that we could refer back to the rep num table. Another case of functional dependence. In this case, this is like the order table. And we know that in our TAL distributors database, we have an order line table that has an order number and a part number, and it's a compound primary key. In other words, the 2 values together are unique, but individually they're not unique. So in the order line table, these 2 columns are unique, and we could consider, and they are a primary key. And then the rest of these columns are non-key values. So here are a couple of problems here. One problem is that the deluxe iron, the part description, is not dependent on the entire primary key. It's only dependent on the part num key. So this is a problem because we don't need the order number to determine the name of the part. We only need the part num key. And so we'll find when we look at normalization that we would remove this column. Here's another issue here. We have the number ordered and the quoted price. If we multiply the number ordered times quoted price, we would have an extended price. So these 2 columns here determine this column. But the rule is that the primary key has to determine all the non-key columns, and it doesn't in this case. So we'll actually examine this in a lot more detail when we talk about normalization, first, second, and third normal rules. Okay, primary and candidate keys. Primary key definition, 1 or more attributes that functionally determine all the other attributes in a relation. Candidate key definition is the same as the above. The concepts of functional dependence and determinants can be used to help in the design of relations. And to finish up, 4 rules for good table design. Each field in a table should represent a unique type of information. Each table must have a unique identifier or a primary key that is made up of 1 or more fields in a table. For each unique primary key value, the values in the data columns must be relevant to and must completely describe the subject of the table. You must be able to make changes to the data in any field other than to the primary key without affecting data in any other field. And that's a key one. You must be able to make changes in one non-key column that does not affect data in another non-key column. So for now, that's functional dependence, and we will continue this in a subsequent video where we talk about normalization for second and third normal form.